Have you ever wondered how your computer works? How your cell phone continues to get smaller, yet have more features? Why electronics seem to be virtually everywhere? The answer can be traced to one innovation, the microchip. Often referred to as the integrated circuit or semiconductor chip, the microchip is a powerful tool in bringing more portable and affordable devices to everyone around the world. Typically, there are over 350 process steps required to make a microchip. For the purpose of this presentation, only the basics will be covered. Microchips are made up of large numbers of small circuit elements known as transistors. A microchip can contain from hundreds to nearly 1 billion transistors. In order to fit all of these circuits on a microchip, they must be extremely small. Historically, circuits have been measured in microns, or 1,000th of 1 millimeter, approximately 70 times smaller than the width of a human hair. Today's advanced technologies produce circuits so small they are measured in nanometers, or 1,000th of 1 micron. That is thousands of times smaller than the width of a human hair. Transistors in digital circuits operate similar to a light switch. They turn the current on and off. This on-off switching is how information is managed and controls how information is stored in a microchip. Electronic circuits consist of two parts. One is the switch, a device that starts and stops the flow of electrical current by either completing or breaking the circuit's pathway. The other is the wire, the circuit pathway which connects the switches to form the circuit. Materials through which electricity flows with relative ease are called conductors. Copper and other metals are examples of conductive materials. In contrast, a material that does not allow electrons to flow through it is called an insulator. For example, glass. Semiconducting materials are unique because they can be both an insulator and a conductor, hence the term semiconductor. A transistor is formed with semiconducting areas that allow the flow of electricity, and insulating areas that don't allow the flow of electricity. Transistors are the fundamental building blocks of a microchip and are built on a silicon base. Silicon is one of the most common elements on Earth, and its unique electrical properties have made it the most commonly used semiconductor. To manufacture the silicon wafer, sand and other materials are processed at high temperatures to purify the silicon. A seed crystal, or single crystal, is brought into contact with the highly purified molten silicon. The seed is slowly rotated and pulled from the crucible, producing a large silicon cylinder called an ingot. When completed, these cylinders can be nearly 5 feet long and weigh hundreds of pounds. The ingot is then sliced and polished into thin discs called wafers, approximately the thickness of a credit card, which then become the foundation of a microchip. The diameter of wafers has grown over time, starting at less than 2 inches in 1970 to 300 millimeters, or the equivalent of 12 inches today. The larger the wafer, the more microchips that can be made at one time. Typically, 200 to several thousand microchips can be made on a single 300 millimeter wafer. There are several basic process steps that are used repeatedly in the creation of a microchip. 3 of the most important steps are film deposition, where a thin layer or film is deposited on the wafer; photolithography, where a pattern of the microchip structure is created when a layer of photoresist is exposed to ultraviolet light; and film removal, where the exposed areas of the wafer are etched away while areas protected by photoresist are not, leaving a pattern on the wafer. These processes are repeated many times, building layer upon layer to make the microchip. Film deposition consists of creating thin, uniform layers of a material on the wafer surface. There are 3 primary techniques for film deposition: chemical vapor deposition, CVD, physical vapor deposition, PVD, and electrochemical plating, ECP. CVD is a chemical process and can be used to deposit both insulating and conducting films. During CVD processing, gases containing elements or components of the material to be deposited on the wafer are introduced into a chamber where a chemical reaction occurs to form a solid thin film on the wafer. On certain microchips, such as microprocessors, the first layer formed uses a CVD process called epitaxial deposition, or EPI. EPI involves growing a layer of high-quality single-crystal silicon directly on a wafer, creating better electrical properties, which results in enhanced performance for advanced microchips. A thin layer of insulating film is deposited on the EPI, forming the foundation of the transistor. The next process is photolithography, a process where a mask with the pattern of one layer of a microchip circuitry is positioned in a precise location above the wafer. This process, also referred to as patterning, is repeated many times during the entire microchip making process. In photolithography, the wafer is first coated with a light-sensitive material called photoresist. The mask is then placed above the wafer and ultraviolet light is flashed through it, exposing the photoresist in select areas, creating a pattern. Each layer of a microchip uses a mask with a different pattern. To ensure that all layers are aligned with each other and that every microchip is the same, the size and pattern of the shapes on the wafer must be exact. To achieve this, a high-precision optical lithography tool steps through every microchip on the wafer, exposing the pattern, one microchip at a time. The photoresist in the exposed areas is then removed, revealing the wafer surface beneath. The material from the exposed wafer surface is then chemically removed, leaving a three-dimensional pattern on the wafer. This process, known as etch, transfers the desired pattern from the photoresist to the wafer, the pattern of a circuit. Once the etch step is completed, the remaining photoresist is removed. The next step in creating the transistor is ion implantation. Extremely small amounts of impurities, called dopants, are accelerated to a high velocity so they can penetrate or implant the wafer surface, changing the electrical properties of the silicon. The wafer then goes through a high-temperature anneal known as rapid thermal processing, or RTP. RTP activates the dopants, changing the semiconducting nature of the silicon, and repairs the silicon crystal structure that was damaged during the implantation step. During this process, the wafer is exposed to a highly controlled thermal cycle that heats the wafer from room temperature to as high as 1,100 degrees Celsius within seconds. There are many implantation and annealing steps involved in the creation of the transistor. Once the transistors are made, they are connected with many levels of metal wiring, called interconnects, which are separated from each other using insulators. The final combination of the transistors and interconnects forms the structure known as an integrated circuit. Today's most advanced logic devices use copper interconnects. Aluminum interconnects are most commonly used in memory chips. There are several common methods required to create these interconnect layers: CVD, PVD, and ECP. To make the interconnect, an initial insulating layer of oxide is deposited between the transistors and the first layer of interconnects to prevent shorting out the circuits. The transistors are connected to the first layer of interconnects through openings in the insulating layer called contacts. These contacts are different from all of the other layers of interconnects because they touch the transistor directly. Once the contacts are completed, the deposition, photolithography, and etching steps are repeated in the successive interconnect layers. One method to deposit metal on a wafer is through physical vapor deposition, or PVD. In a high vacuum environment, a gas is accelerated toward a metal target. This target material is the source of the metal atoms that will make up the conducting film on the wafer. Metals commonly used are aluminum, copper, and titanium. The accelerated gas is directed at the metal target and physically knocks off tiny amounts of the metal material, depositing a thin layer of the desired material on the wafer. A second method of depositing metal is atomic layer deposition, or ALD. ALD is a new emerging type of CVD, capable of forming extremely thin layers. In ALD, chemicals are introduced sequentially into a low-pressure chamber. The resulting chemical reaction creates an ultra-thin layer of material. Each such deposition cycle deposits a thickness equivalent to a single atomic layer. By repeating the number of cycles, the desired film thickness is achieved. Ultra-thin films can thus be deposited with precise control. A third method is electrochemical plating, or ECP. In ECP, the wafer is immersed in a solution containing dissolved copper. A voltage applied between the solution and the wafer pulls the dissolved copper to the wafer, depositing the copper film. This plating process continues until the desired thickness of copper is achieved. The ECP deposition step leaves the surface uneven, making it difficult to pattern the wafer for the following interconnect layer. To smooth the entire surface of the wafer, a process called chemical mechanical planarization, or CMP, is used. The next photolithography step now has a flat surface on which to create the pattern for the subsequent layer of the microchip. CMP is both a chemical and a mechanical process. During CMP, the circuit side is held against a rotating pad while an abrasive liquid chemical, called slurry, is added. After the deposition of the metal is completed and the surface is smoothed out with the CMP step, another layer of insulating material is deposited between every interconnect layer to prevent shorting out the metal lines on the microchip. These process steps are repeated until all the interconnects have been created and the microchip structure is complete. Today's most advanced microchips can have up to 10 layers of interconnects. Because a single process wafer can have a value of tens of thousands of dollars, it becomes increasingly important to verify the integrity of each process step, and if errors are found, they must be immediately corrected. Various metrology and inspection steps are used to monitor wafer manufacturing processes throughout the fabrication sequence. Metrology and inspection technologies include defect inspection, DRSEM, defect review scanning electron microscopy, and CDSEM, critical dimension scanning electron microscopy. Defect inspection locates defects on the patterned wafers. DRSEMs use electrons to image and then automatically classify defects on the wafer, such as particles, scratches, or residues, enabling engineers to determine the source of the defect. CDSEMs measure the critical dimension of the sub-micron-sized circuits in a microchip, assuring the accuracy of the manufacturing process. CD measurements are typically performed after the photolithography and etch steps. All of this processing has to be done in extremely clean manufacturing facilities called fabrication plants, or fabs. Because a single particle of dust can destroy a microchip, the air in the fabs is 2 million times cleaner than the air we breathe in our homes. To keep the air in a fab clean, portions of the building are sectioned into areas called clean rooms, and special clothing, commonly called bunny suits, are worn by the engineers who work inside. Bunny suits are made of a special material that stops hair and skin particles from getting into the air. In some ultra-clean clean rooms, engineers must wear breathing apparatus to clean the air they exhale. Once all the processing steps are completed, the wafer is cut into individual microchips, which are then tested, packaged, and assembled. Microchips are then shipped around the globe and are incorporated into the devices we use every day. When you pick up the phone, turn on a computer, start your car, or watch television, it is the microchip that enables these devices which shape today's modern society. With the broadest product line in the industry, Applied Materials makes the equipment used by chip makers to create smaller and more powerful microchips.